Hello again and welcome back. Today we are in section 3.2 and we'll be talking today about measures of dispersion or measures of spread. So we'll learn about how to determine the range of a variable from raw data. We'll talk about how to determine the standard deviation of a variable from raw data and how to determine the variance of a variable from raw data. And I'll also show you the empirical rule, which is a kind of a useful rule of thumb that you can use when you have data that fits a bell-shaped distribution. So here we go. Now let's jump right into example 1. Here we have a set of data for University A and a second set of data for University B. If we were to take the time to put both of these giant data sets into our calculators, we would find out that both data sets have the same mean. However, you can tell by looking at the histograms that the data for University A has a larger spread than the data for University B. And that's what we want to talk about in this section. We're talking about measures of dispersion or measures of spread. Now there are three commonly used measures of dispersion: range, variance, and standard deviation. The simplest measure of dispersion is range. The range, denoted by the letter R, is the difference between the largest and the smallest data values. In other words, R equals the largest value minus the smallest value. So here we have an example. Here's a data set, and this is the same one we've been using. It says the data in the table represent the scores on the first exam of 10 students enrolled in introductory stats. Compute the range. So we'll need to look through the table and find the largest value, which appears to be this one, 94, and then the smallest value is 62. So the range is going to be 94 minus 62, which of course is 32. So the range here is 32. So of course you've noticed that the range is computed using only the largest and smallest values, and that means that the range is very strongly affected by extreme values. So that means the range is not resistant. Now let's look at our second measure of dispersion, which is going to be standard deviation. So keep in mind that measures of dispersion are meant to describe how spread out the data are. So standard deviation is another measure of dispersion, and it's based on the deviation about the mean. So what do I mean by deviation? Well, for each data value, the deviation from the mean is the difference between the given data value and the mean. Now it seems like, if you think about it, that it would be nice to have a measure of dispersion that would give us the average of all the deviations, and that way we would have an idea of what a typical deviation is. But it turns out that that's not so helpful after all, because the sum of all the deviations from the mean is always going to be 0 because of the way mean is calculated. You see, some of the deviations will be positive and some of the deviations will be negative, so they're always going to add up to 0. Now what we could do to fix this problem is to square each of the deviations and then add the squares together. This is helpful because a squared number is always positive. So whereas the sum of the deviations was always 0, the sum of the squares will not be 0. And then we can divide the sum of the squares by capital N, which is our population size, and we can take the square root of the whole thing to reverse the squaring process. The resulting value is called population standard deviation. So now here's the formula for population standard deviation, and notice that it has a Greek letter for its symbol because it is a population value. The Greek letter lowercase sigma always stands for population standard deviation. So S for sigma, S for standard. Now I don't want you to get confused. This was capital sigma and this symbol stands for sum. But this is lowercase sigma and this stands for population standard deviation. And the way we read this formula is first we find each value's deviation from the mean. So we take each data value and we subtract the mean from it, and that is the deviation. Then we square each of the deviations, and we'll have a squared deviation then for each data value in our data set. And then we find the sum of the squared deviations, and we divide that sum by the population size, and finally we take the square root of the whole thing. And that's how we find population standard deviation. So here is example 3, and we are going to try out our new standard deviation formula. This example says use the conceptual formula to calculate the population standard deviation of the following population of test scores. And here we have only 5 numbers in our population. As you can imagine, this formula can get pretty tedious the bigger your data set is. So we're only going to do it on relatively small data sets. First of all, you know from looking at the formula that you need to find the mean of the data set before you can find each value's deviation from the mean. So I've already put these 5 numbers in my calculator, and I have calculated that the mean of this population is 83.4. So now what I'm going to do is list each of the values in my data set, and in the next column I'm going to calculate the deviation for each value. So I'm going to say 72 minus 83.4 is negative 11.4, and then 84 minus 83.4 is 0.6, and then 96 minus 83.4 is 12.6, and then 86 minus 83.4 is 2.6, and 79 minus 83.4 is negative 4.4. And you don't have to do it, but I just want you to take a second to appreciate the fact that since some of these are positive and some of them are negative, they are going to add up to 0. Okay, so that's why the formula has us take the deviations and square each one. So now I'm going to make myself another column, and I'm going to square each of the deviations. So now negative 11.4 times negative 11.4 is 129.96. 0.6 squared is 0.36. This number squared is 158.76. And then we have 6.76 and 19.36. Okay, now when you read the formula, can you tell what to do next? The formula says to sum all of the squared deviations. So I'm going to add together all of the numbers in this column, and the sum of the squared deviations is 315.2. Okay, now let's take a look at our whole formula. We take the sum of the squared deviations, we divide by the population size, and then we take the square root of the whole thing. So I know now that the value of the top part of the formula is 315.2, and the value of the bottom part is population size, which is 5. And then the formula says to put all of that under a radical. And you can enter this in your calculator now and say square root of 315.2 over 5 is 7.9. And notice we've used our rounding rule again. The original data set had no decimal places, but our calculated standard deviation has 1 decimal place. Okay, now I would like to talk to you about 2 things. One is showing your work. You know that probably on a quiz or maybe even on the midterm exam or the final exam, you're going to be asked to show your work on a problem where you have to use the standard deviation formula. And this is how you should do it. This is the easiest way to lay it out. So first list your data values, then do each of the deviations, then square each of the deviations. And you don't need to memorize this because you can read it from the formula. First you need the values, then you need the deviations, then you need the squares of the deviations, then you need the sum of the squared deviations. So then you can sum this third column like I did here. And then when you found that sum, you can come over here and say, okay, population standard deviation is this formula the top expression gets replaced by this number, and the population size is this, and then it's an easy hop from here to the calculator to get the final value. And the other thing I wanted to talk to you about is how to use the list editor on the calculator to speed up some of this work for you so that you're not punching in minus 83.4 5 times, and so that you're not having to enter each of these numbers and square it. And it's just going to minimize your work. So let's flip over now to the calculator. Okay, so here I have my calculator pulled up, and you can see that I've already entered our 5 numbers into my list 1. And what I want to do here is recreate the columns that I showed you on the last slide here in my list editor. And I can automate some of that calculating. So look at our formula and see that the first thing we have to do is each data value minus the mean. Okay, so you could certainly click Stat here and then arrow over to the Calc menu and run one variable stats, and you see that the mean of this data set is 83.4. So you could just write that number down if you want to and use it, but I'm going to even show you a little shortcut on top of that. So first of all, if you want to enter a formula into a list, what you need to do is put the cursor up in the title of the list. So I'm going to actually come here and click up arrow, and that's very important that you see that the list title is selected. And now I can enter a formula here, and it will calculate each value in list 2 based on the values in list 1. So what I want to happen here is each number from list 1 minus the mean, which was 83.4. So I'm going to say second 1, which puts L1 right here, and then I want to say minus 83.4. And then enter, and notice that it calculates all 5 of them for me instantly, so I'm not having to do each one individually. I just love that it does that automatically. And let me clear that list out now and show you something else. If I didn't already know that the number was 83.4, what I could do is, again, up arrow so that L2 is selected, and I can tell it to do each number from list 1 minus the mean of list 1. So now I can say minus, to get it to do the mean of list 1 automatically, you can use this list menu here. Do you see that in blue? So I can say second list, and now here we have all things that have to do with lists. So what I can do is arrow over to the Math submenu, and you see my third choice is mean, so I can do that. And so now I want each number from list 1 minus the mean of list 1. So I'm going to go second L1, enter, and there you see that time it did the same thing, but it did it without me having to run one variable stats first to find out the mean. So you don't have to remember that, but in case you're handy with the calculator and you wanted to know that, there it is. Okay, so now over in list 3, what we want to do is get the calculator to square each of the numbers from list 2. You see from the formula, square the deviations. So how am I going to get the calculator to square each of these numbers? Well, I'm going to arrow up so that L3 is selected, and then tell it that I want L3 to be made of each of the numbers from L2 squared, and then enter, and it's going to automatically square each of the numbers from L2. And now it'll be easy to get the sum of these numbers because all I have to do is run one variable stats on list 3. So I'm going to say stat calc one variable stats, and now if you had the old operating system you could say L3 here, but I don't have the old one, I have the new one. Still, I'm going to change the list location to L3. So second 3, you can still leave frequency list blank and scroll on down and press enter. And so now we see that the sum is 315.2. So now I can say that the square root of 315.2 divided by 5 equals 7.9, and there's the 7.9 that we found when we did it ourselves. So I just wanted to show you that. Only use it if it's helpful to you. Otherwise, if you are more comfortable just plugging away on the calculator, that's fine, because we're not going to have to do this very often. But I did want to show you that, because as long as you've got the calculator, you might as well know all the tricks. Now we're going to talk about sample standard deviation. And sample standard deviation is denoted by the letter S, lowercase s. So remember, Greek letters are for population values, so we had lowercase sigma for population standard deviation, and sample values or statistics are denoted by Roman letters, so we have lowercase s for sample standard deviation. And for sample standard deviation, we divide by n minus 1 instead of capital N. So remember, when we had population standard deviation, we divided the sum of the squared deviations by the population size. But here, with sample standard deviation, we're going to divide that sum of squared deviations not by sample size, but by sample size minus 1. And that means that the number we get for sample standard deviation will not be identical to the number we get for population standard deviation. Unlike population mean and sample mean, these two values have different formulas, so they are not going to be the same number. It's important to note that population standard deviation and sample standard deviation are not the same value. Now, the basic idea behind standard deviation is that it is approximately the average difference between each data value and the mean. In other words, it's the typical deviation from the mean. And here is the formula for sample standard deviation. Lowercase s is equal to the square root of the sum of the squared deviations divided by sample size minus 1. So notice here, we're not subtracting the population mean from each value because we don't have a population, we have a sample. So we're subtracting the sample mean from each value. And let's do an example together. So reading the formula, we see that the first thing we should do is subtract the mean from each data value. So the first thing you should do is average these four numbers, and you'll see that the sample mean is 80. Okay, now let's list our four numbers, and then according to the formula, the next thing we should do is subtract the sample mean from each of those numbers. So the deviations are 90 minus 80 is 10, 77 minus 80 is negative 3, 71 minus 80 is negative 9, and 82 minus 80 is 2. And then the formula says we should square each of those deviations. So 10 squared is 100, negative 3 squared is 9, negative 9 squared is 81, and 2 squared is 4. And then the formula says we should sum the squares. So we'll add all of the numbers in this column together, and the sum of that third column is 194. Okay, now let's take that and plug it into our formula. So I'm going to recopy our formula over here, and then I'm going to say this top expression is equal to 194, and the bottom expression is sample size minus 1, so that's 4 minus 1, and it's all under a radical. And now we know 4 minus 1 is equal to 3, and so now on your calculator, the square root of 194 over 3 is equal to 8.0, and I did keep one decimal place because the data does not have any decimal places, so my calculated statistic should have one decimal place. Now in this example, I would like to show you how to use the statistical functions on the calculator to find the population standard deviation and the sample standard deviation without doing any of the work yourself. All you have to do is enter the numbers. So I have already entered these numbers into my list 1, as you can see here. And so now all we're going to do is run that one variable stats command that we used when we were looking at the mean and the median. So stat calc one variable stats. Again, if you have the old operating system, then your screen now just says one variable stats. And if your data is in list 1, all you have to do is press enter. If your data is not in list 1, you need to use second, whatever number is the appropriate list for where you put your data. But this screen is from the new operating system, and we do need to tell the calculator that we want list 1 analyzed. So I'm going to press second 1 and then arrow down twice and press enter to calculate. Okay, now you're familiar with the mean and the sum of the data, and here's the sum of the squares if you wanted it. And these two values are our standard deviations. Notice we have S for sample standard deviation, and that's going to be 10.3. And then we have lowercase sigma for population standard deviation, and that's going to be 9.8. Now you may be thinking back to the first measure of spread that we looked at, and that was range. And the calculator does not automatically give you range. However, you can scroll down to the next screen and see the min and the max. So in a large data set, this would keep you from having to scan through the data and find the min and max on your own. But once you find the max and the min, you can just on your own say 94 minus 62. Now I want to make sure you understand that it's important that you know how to use the formula, but not so much because we're going to have to use the formula all the time, but mostly because understanding the formula helps you understand what standard deviation really means. And that's the important thing, because moving forward from here on out, we will rely on the calculator's statistical functions to find standard deviation whenever we need it, and we will not ever have to go back to the formula once we get out of Chapter 3. So just a few words about standard deviation. The standard deviation is used along with the mean to numerically describe distributions that are symmetric, because if you have the mean and standard deviation, then you have the center and spread of a data set, and those are two of the most important characteristics. So you'll see mean and standard deviation used to describe symmetric data, and then you'll typically see other values used to describe skewed data. And again, basically the standard deviation represents the typical deviation from the mean. The larger the standard deviation, the more dispersion or spread the distribution has, provided the populations have the same unit of measure. And now our third and final measure of dispersion for this section. This is variance. The variance of a variable is simply the square of the standard deviation. And the population variance is denoted by sigma squared, and the sample variance is denoted by S squared. So this is right in line with what we already knew about standard deviation. Remember, population standard deviation was lowercase sigma, and now since variance is the square of the standard deviation, the symbol for population variance is sigma squared. That makes perfect sense. And the symbol for sample variance is S squared. Now, variance is not typically used to describe a data set because it has to be represented in square units, and that makes it difficult to interpret. However, we mention it here because it does appear in formulas that are used in certain types of statistical inference. So here's example 7, and we're going to take the standard deviations that we found in examples 3 and 4 and use those to find variance. So in example 3, we found a population standard deviation of 7.9, and therefore variance is 7.9 squared, in other words, 62.4. And in example 4, we found a sample standard deviation of 8, so sample variance would be 8 squared, which is 64. Now we're going to get to talk about the empirical rule. This is just a rule of thumb that's going to help us estimate the percentage of data that lies within a certain distance of the mean. So this says if data have a distribution that is bell-shaped, the empirical rule can be used to estimate the percentage of data that lie within 1, 2, or 3 standard deviations of the mean. Okay, now a couple of things. It's important to remember that the empirical rule only applies to bell-shaped data. This would not apply to a data set that has a skewed distribution. And also, the word empirical means observed. So this rule does not have to be derived from some mathematical concept. It can be just observed by handling several bell-shaped data sets. And let me show you what we're talking about here. So the empirical rule comes in 3 parts. And it says if a distribution is roughly bell-shaped, then approximately 68% of the data will lie within 1 standard deviation of the mean. That is, approximately 68% of the data lie between mu minus 1 sigma and mu plus 1 sigma. And remember, sigma stands for standard deviation. Now I want you to take a good look at this curve before we get started with the empirical rule. You're going to need to be able to draw your own curves later on, so really think about how the curve is drawn and practice drawing it yourself. So what I always do is start by drawing a flat line, and then I draw the curve above it. Now let me tell you a little about this curve. This curve is meant to symbolize a bell-shaped histogram. And remember that for a symmetrical distribution, we always find the mean in the center of the distribution. So in the center where the distribution is at its highest point, you can label the mean on the horizontal axis. And this point right here is called an inflection point. An inflection point is where the curve stops curving down and begins to curve out. That is, that's where the curve changes direction. And the reason I bring that up is that the inflection point marks the place where we will find mu plus 1 sigma and on the left side mu minus 1 sigma. So the empirical rule tells us that about 68% of the data will lie between mu minus 1 sigma and mu plus 1 sigma. Now take a look at the shaded area here. It's not difficult to believe that the shaded area takes up more than half of the total area under the curve. And in fact, what we're seeing here is that the shaded area takes up about 68% of the area under the curve. And remember, this is a rule of thumb, so it's not going to be exactly 68% for every bell-shaped distribution, but it's approximately 68%. And then the second part says that if a distribution is roughly bell-shaped, then approximately 95% of the data will lie within 2 standard deviations of the mean. That is, approximately 95% lie between mu minus 2 sigma and mu plus 2 sigma. So again, remember that at the inflection point, we have the mu plus 1 sigma mark. If you go out that far again, you'll hit the mu plus 2 sigma mark. And then if we do that on the left side and we shade everything between mu minus 2 sigma and mu plus 2 sigma, then we will cover 95% of the area. Or in other words, 95% of the observations should be within 2 standard deviations of the mean. And again, it's approximate, not exact. And then the third part says that approximately 99.7% of the data will lie within 3 standard deviations of the mean. And notice that's nearly all. So there are not many observations that are more than 3 standard deviations away from the mean. Certainly an observation that's more than 3 standard deviations away is a very unusual observation. So notice that when we go out 3 standard deviations from the mean, if we shade everything that's within 3 standard deviations, we are covering nearly all of the area underneath the curve. Now let's look at a couple of examples together. So this is exercise 30 from your textbook, and it says SAT math scores have a bell-shaped distribution with a mean of 515 and a standard deviation of 114. What percentage of SAT scores is between 401 and 629? Well, let's start by drawing the curve, and that's always a good place to start. So always sketch it for yourself because a picture's worth 1,000 words. And then you know that the mean is going to be right in the center of that curve. So right here at the center, we'll label that 515. Now what we would like to know is how many standard deviations is it from the mean to 401 and from the mean to 629. So let's start by subtracting 515 minus 401, and we see that that is 114. So that is exactly one standard deviation, which means that 401 belongs here at the inflection point. 401 is one standard deviation below the mean. And we can do the same thing for 629. So 629 minus 515 is 114, which means that 629 is exactly one standard deviation above the mean. So its line will go here. And now we know that these two values lie one standard deviation in each direction away from the mean. So what does the empirical rule say about one standard deviation? Well, it says that approximately 68% of the data will lie within one standard deviation of the mean. So therefore, about 68% of the data are between 401 and 629. And here's part B. It says what percentage of SAT scores is less than 401 or greater than 629? So we want to know what percentage of SAT scores is in these tail areas here. Now the area under the curve represents 100% of the data. And we know that 68% of the data are between 401 and 629. And now 100% minus 68% means that 32% of the data are not between 401 and 629. And therefore we can say 32% of the data are either less than 401 or greater than 629. Now let's have a look at part C, which asks us what percentage of SAT scores is greater than 743. So I've drawn our curve and I've put the mean in the middle, 515, and now we want to find out how many standard deviations away from our mean this 743 is. So let's subtract 743 minus 515 and we'll get 228. And the question now is, how many standard deviations does that represent? So if you take 228 and divide it by 114, you'll see that 228 is worth 2 standard deviations. So now I know that 743 belongs out here somewhere. So remember that one standard deviation would be about here at the inflection point, and then I go that far out again, and that represents 2 standard deviations, so that's 743. Now let's go ahead and draw a line back here as well that's also 2 standard deviations away from the mean. And now think about your empirical rule. The empirical rule says that approximately 95% of the data lie within 2 standard deviations of the mean. So now keep in mind that we're trying to find out what percent of the data are greater than 743. What we know right now is that 95% of the data are between these two numbers. That means that 5% of the data are not between those two numbers. So the area in both tails together represents 5% of the data. Now, lucky for us, bell-shaped data is symmetrical, which means that the area in this tail should be the same as the area in this tail. So to find the area in this rightmost tail, all we have to do is take the area in both tails and divide by 2. So we see now that approximately 2.5% of the data can be expected to be greater than 743. And now I've taken another exercise from the book, but I've changed this one a little bit, so if you look in your book, it won't match exactly. But let's take a look at it. It says the distribution of the length of bolts has a bell shape with a mean of 4 inches and a standard deviation of 0.007 inch. And then they ask us, about 68% of bolts manufactured will be between what lengths? Okay, now the reason they tell us that the distribution has a bell shape is so that we can use the empirical rule. Remember that the empirical rule only applies to bell-shaped data. So let's go ahead and draw ourselves a curve, and we remember that the mean is in the center, so we'll draw a line there and label it 4 because that was the mean they gave us. Then we know that the empirical rule tells us that about 68% of the data will be within 1 standard deviation of the mean. So let's take our mean and subtract 1 standard deviation. 4 minus 0.007 gives us 3.993, and 4 plus 0.007 gives us 4.007. So that will be the limits that we put here, 3.993 and 4.007. And now we know from the empirical rule that 68% of the observations should be between those two numbers. And here's part B that says what percentage of bolts will be between 3.986 inches and 4.014 inches. So again, start with a diagram, and now let's find out how many standard deviations it is from the mean to this upper limit. So we'll say 4.014 minus 4, and that gives us, of course, 0.014. Now, how many standard deviations is that? If you divide this number by the standard deviation, you'll find out that that represents 2 standard deviations. And then we can do the same thing for 3.986. So 4 minus 3.986 also gives us 0.014, and of course that's still 2 standard deviations. So now we can draw our 2 lines here, both 2 standard deviations away from the mean, and we can label them 3.986 and 4.014, and we know that the empirical rule says that approximately 95% of the data will be within 2 standard deviations of the mean. And here's part C. If the company discards any bolts that are less than 3.986 inches or greater than 4.014 inches, what percentage of bolts will be discarded? Well, we've already figured out that these 2 numbers are 2 standard deviations away from the mean, and we know that 95% of the observations should be between those 2 numbers. So these bolts out here in the yellow areas are the bolts that are going to be discarded. So if 95% are between these 2 numbers, then of course 100% minus 95% means that 5% are not between those 2 numbers. So about 5% of the bolts would be discarded. And part D, 99.7% of all bolts manufactured will be between what 2 lengths? Well, we know from the empirical rule that 99.7% of all observations will be within 3 standard deviations of the mean. So to find the lower limit of this range, we'll say the mean minus 3 standard deviations, and we find that that is 3.979. And to find the upper limit of that range, we would say the mean plus 3 standard deviations, and that's going to be 4.021. So 99.7% of all the bolts manufactured should be between 3.979 and 4.021.